Hello. So we've been talking a bit about partial derivatives, and I'm going to continue with that. And this is just sort of some, I don't want to call them odds and ends because they're not necessarily unimportant. They're just uh, not as clear a through line between them. So just several little ideas that I want to finish up this section with. So the first is one that I won't go very much further with in any further videos, but you should understand. Has to do with, we've been looking at functions of two variables, but we can extend all these ideas to functions of more than two variables. So for instance, if I have a function like f of x, y, z, right? So here's a function with three input variables. I can define in the same way as we defined for our functions of two variables, a derivative for the variable x, for instance, right? We can do this for all of them. That would look something like limit as h goes to 0 is going to be f of x plus h comma y comma z minus f of x, y, z all over h. Right, the idea being exactly the same as it was before. We're holding the other two variables constant and just manipulating this variable, in this case x, right? And you can extend this to 10 variables. If you have 10 inputs, you vary one of them for your limit definition of the derivative of that particular variable and hold all the others constant. Okay, so I'm not going to go through all the definitions for the x, y, and z derivative. They look the same. You can look back at how we did it for x and y in the previous video. But let's just do one example. Let's look at a function of three variables. Let's call it xy squared sine of yz. And I will mention, these are very difficult to graph and to picture, right? So let's just think about our functions that we've seen in the past. You have functions of a single variable, right? And what do their graphs look like? That's how we picture them. Well, their graphs are curves, right? Curves are one-dimensional objects, and we draw them in a two-dimensional space, right? The xy plane is 2 dimensions, and the curves themselves are one dimension, like lines, right? And then when we get to functions of two variables, their graphs are surfaces, two-dimensional objects, and we draw them in three-dimensional spaces. Well, functions of three variables would be three-dimensional objects, and we can only draw those in four-dimensional spaces. And we don't have those, right? We don't have access to those spaces exactly. There's a couple ways people do things like this. The third dimension or the fourth dimension can often be time, so you can sometimes draw these as essentially level curves where you're doing it for each the level that you're looking at are slices in time, and these things might evolve over time, is one way to do it. But we're not going to dig deep into that notion, right? And then certainly when you get up to 10-dimensional functions, we really run out of ways to picture them and just have to use what we've learned in these easily picturable numbers of dimensions. You know, we translate ideas from them over to these higher dimensional problems. And just to be clear, higher dimensional doesn't necessarily mean some kind of like sci-fi adventure. It just means that I'm using it in a loose sense here, and we're using it to think of the number of variables that affect our output, right? And so that can be a very mundane operation. If you run a factory, you might have an efficiency function that has to do with things like, you know, attendance of your workers and the lighting conditions that day. Maybe you're in whatever. There could be a whole bunch of variables: the air quality, the transit situation in your city. All these different things that might play into how much production you can do on any given day. Or when you're dealing with weather systems, right? Predicting the temperature at a certain point at a certain time requires you to know lots and lots of inputs, right? So things like the current temperature, temperatures in areas nearby, the wind amount and the wind direction, air pressure, humidity, all these kinds of things. So you can make a list of a huge number of dimensions to the problem. It doesn't mean we have to necessarily live in some kind of, 11-dimensional sci-fi space. It's just the number of things that are inputs. anyways, let's just take one practice taking partial derivatives of a function with 3 variables. So if I take the derivative with respect to x, right, all of this stuff over here is treated just like a constant, because that's what we do when we take partial derivatives. We treat everything that's not the variable in question like a constant. So it's x times a constant, and the derivative is just that constant, right? So that's our x derivative. Our y derivative becomes a little more complicated, right? I'm thinking of it as I've got a function of y out here and a function of y out here, so I have to do a product rule. I'll take the derivative of this first function here, which is the constant x, right? It's not really a constant, but I'm thinking of it that way, times y squared. So I get 2xy, right? That's just the power rule, taking down the 2. And I leave this alone. Now, I'm finishing my product rule. I leave the first function alone, and I need to take the derivative of this second function. Here we have a chain rule. So we take the derivative of sine is cosine of yz. But then the chain rule tells me I have to take the derivative of this inner function, which is y times a constant, and I just get the constant. Okay? If we want to pretty this up a little bit, I might write something like 2xy sine of yz plus xy squared z cosine of yz. You could factor out an x and a y if you wanted, if you thought that was a little nicer. In any event, either of these are reasonable expressions for this derivative. And then finally, the derivative in the z direction. Well, we've got nothing with z out here, and all we have is z in here. So everything we're looking at is a constant, but that z. So I'm going to get xy squared cosine. So I'm taking the derivative, right? The xy squared are like a constant times sine, and this would just stay while I take the derivative of sine. But again, I have a chain rule. This time y is playing the role of the constant. Y is playing the role of the constant. Z is the variable. So I multiply by y. I'm just going to absorb it into this y squared and make it a y cubed. And that gives us our three partial derivatives. Okay. All right. So that's about all I'm going to do with functions of more than 2 variables for now. Let's look into some other ideas. So one thing we should notice, right, when I have a function like z equals f of xy, when I take the derivative, let's use this notation. Some people say things like del z, del x, or the partial z, partial x. That's what I usually say. Remember, this is just another notation for x, the x derivative. Notice, though, this is still a function of 2 variables. Just like if I look over here at the ones we just did, the functions that we spit out are still functions of several variables. They're functions in and of themselves, right? Just like with variables, functions of single variables, when we take derivatives, we can go take other derivatives. We can do that here as well. Okay. So let's organize this a little bit. So let's say, I'm going to just erase what I just wrote here. 1 second. So we're going to have 4 second derivatives now, though, right? So I guess I didn't want to erase what I just did. Let's see if it comes back. Oh, it is coming back. Sorry, I just changed my mind. Right? So we can start by taking two partial derivatives of this function, del z, del y, or partial z, partial y. This one's fy, x, y. But each of these, like I said, is still going to be functions of 2 variables, right? So what can I do? I can take a second derivative. I take this partial with respect to x, and I do the partial with respect to x again, right? This is my function in here that's got the first derivative taken. I put that little x there again to say I'm taking the derivative again. Sometimes we write it this way, right? What does this mean? Here's all of our notations. That's telling us to take, here's the partial with respect to x, and it says take a partial with respect to x again. Sometimes we write things like this, del squared f del x squared, or del squared z del x squared. That's a little 2 there. Okay, so there's several notations for the same thing. But we could also take that function of 2 variables and take a derivative with respect to y. All right, and again, we get a whole bunch of different notations, but they all mean the same thing, right? I think in this point, maybe this one is the clearest, that this is saying, here's a function of x and y that happens to be the x derivative of a function of 2 variables. Take the y derivative of it, right? That's pretty clear there, right? This, you just kind of have to remember the order. This is f sub x is the x derivative, and then we're doing the y derivative to it. Okay. Or we can use this. We'll get looking like that. Or if we like z, that will work as well. Okay. And then we can do all the same things with the y derivatives. I can take an x derivative of the y derivative to get my second. Sometimes we call these the mixed partials, right? You're taking a partial in each direction, the x and the y direction. And so now this is taking the y derivative first and then taking the x derivative. 2's are not coming out well. Okay, and then finally, you can take the y derivative and then take the y derivative again, and you get all the same kinds of notations. And there we have it. Okay, so whole bunch of notation, but really just a couple of big ideas in here, right? And they're really the same as taking the derivatives we've already done. So let's do an example running through all of these kinds of derivatives. So here's a function. Let's take the function f of xy is equal to x squared y cubed plus x. Okay. So first, we can take our x derivative. I'm treating y as a constant. This is 2x y cubed plus 1. And my y derivative, what am I going to get? I'll get 3x squared y squared, right? X is like a constant, so here, when we take the derivative of y cubed, we bring the 3 down and leave that constant there, but the x just disappears, that extra x at the end, because it's a constant and they go away in the derivatives. All right, so now for each of these, I have each, look at these two functions. They're both functions of x and of y. And so for each of these, I can take an x derivative and a y derivative. So let's start with the x partial, the first partial derivative with respect to x, and take another x derivative, right? So I'm looking at this 2xy cubed plus 1, treating x as my variable, everything else is a constant, and I end up with 2y cubed. Let's take a second y derivative here. Again, 3x squared is a constant, so I'm taking a derivative with respect to y. The 2 comes down, I get 6x squared, and y stays there. Now I take my x derivative, my first partial with respect to x, and then take a y derivative of it, right? So I'm looking at this this piece right here. Oh, sorry, I looked at the wrong place in my notes. Sorry for that dramatic pause. There's nothing dramatic about to happen. I just misread something in my notes and thought I messed everything up. Pardon me. So I'm taking the y derivative of, just to make sure it's clear, we're looking at this derivative up here. So I've got my partial derivative with respect to x, and now I'm taking a partial derivative with respect to y. So now I'm looking at 2xy cubed plus 1, treating y as my variable, x as a constant. So this 3 comes down, multiplied by the 2 gives me 6, multiplied by the constant x, that's in quotes, x is not a constant, but we're treating it like 1, and I get y squared, 6xy squared. And let's do the same thing over here. We've got a y derivative, let's take the x partial derivative of it. So again, I'm looking back up at this first row, taking this derivative, taking a derivative with respect to x of 3x squared y squared. So now y is playing the role of a constant. X squared gets the derivative, we pull the 2 down, it gets multiplied by the 3. Its power becomes 1, and we're left with a y squared treated like a constant. Okay? And so there are our 4 second derivatives. Right? We get 4 derivatives here. A couple things I want to point out. First of all, we can expand this. I can start taking third derivatives, right? I'm not going to do that right now, but again, look at these things. They're all still functions of 2 derivatives, of 2 variables. Even this one over here, for instance, 2y cubed, I'm still living in this two variable space. So its derivative, for instance, if I took a third derivative with respect to x right here, it would be 0, right? I just treat y like a constant. It's just a constant, we get 0, but we still think of it as a function of 2 derivatives, right? We might also be noticing that these 2 derivatives are equal, right? And that is not an accident. I didn't work hard to set that up to make that happen. There is a theorem called Kleros. I do not know if I am pronouncing / spelling this correctly. Kleros Theorem, which states, essentially just states, if the second partial derivatives, if the mixed partial derivatives, meaning the one that's in the direction of x and the direction of y, and then one that's in the partial with respect to y, partial with respect to x, those mixed partials, if they exist and are continuous, they're always going to be equal, right? And so it's not hard to find functions where this is not the case, but it's not typical, right? So most of the nice kinds of functions we deal with, polynomials, rational functions, those kinds of things, generally these mixed partials are going to be equal, except for at points where, for instance, maybe you have like zeros in the denominator and the functions explode, or things like this. We'll look at some examples, or creases when you have corners and things like that. You can end up with mixed partials that are not equal. But most of the well-behaved functions we're going to look at do not have those problems, okay? So what we can say this more specifically, if we say that suppose a function f is defined on a disk D, containing the point AB. So suppose f is defined on a disk D containing AB if the mixed partials are both continuous on D, then they're equal to each other, right? Okay, so it's a nice, convenient thing that they're equal to each other. Certainly, it helps us check our work if you ever are working and they're not. It's reasonable to suspect that something has gone wrong, though you might be dealing with a function where they're not equal, but then there should be some reason for it. You should see something kind of special happening at that place. Okay, let's do one more thing. We looked a little bit at, sorry about that. We looked a little bit at sort of interpreting what these partial derivatives were telling us. I want to give a slightly different interpretation of them than we did in the last video. Right? I looked at like slices and tangent lines in certain planes at those slices in the last video, which is definitely a good way, and we're about to do a whole bunch with that idea in the next section and in our next videos. But there is another thing, right? Just like one way we use derivatives in single variable calculus is to get slopes of tangent lines, but also we just use them to give us a general idea about behavior of graphs. So here I'm looking at the function z equals x squared plus y squared, x squared plus 1 over y squared plus 1. I can take the partial with respect to x. I get 2x over y squared plus 1. I can take the partial with respect to y. This one's a little bit more complicated. I think it works out to be, and I'm leaving this as a nice exercise for you to see why these are the way they are. But there are our two partial derivatives, first derivatives. Okay, so let me just put these a little bit off to the side. So these can also be thought of as telling us stuff about telling us information about the shape of this graph, right? So this is a graph of the function. Okay. It's got lots of interesting properties to it, lots of interesting curves and shapes. I'm just going to scale down a little bit so it's not, oops, I went the wrong way. Anyways. All right, so here we are looking at it. Let's look at a graph of the partial with respect to x. So here's, actually, let's do one thing first, sorry. Let me get these oriented correctly. So now the x-axis is the red one, and it is, the positive direction is off to the left here. So I want to imagine, for instance, right, what the derivative with respect to x is supposed to tell us is, if I change x in a positive way, how does y change? So for instance, if I'm sitting at this point right here, and I move in the positive x direction, I can see that I'm going up. And if I'm sitting over here and I move in the positive x direction along this line, it looks like I'm going down. So what we should expect is that the values of our derivative with respect to x by this point should be negative or positive, and the ones over here should be negative. So let me turn that graph on. And that's exactly what we see. It's tricky. This purple graph is living underneath this one, but notice that where it looked like the hill, the way we move in the positive x direction is going up, we have positive values. If we also notice, right, if I picked a point over here and moved in the positive x direction, it's much steeper, signifying a bigger slope of that like tangent line living in the slicing plane. And you see higher values of our partial derivative versus over here where it gets a steeper slope down. You can see this purple shape going down and getting increasingly negative, right? So it matches that kind of same kinds of intuitions that we did in single variable calculus. Also notice, let's do one other thing here. I'm going to zoom out for a second. Notice that the red shape, the function itself, gets very, very flat the further away from the origin out on this y-axis we get, right? As I go further and further out on the y-axis, it's getting flatter and flatter. We would expect the slope to be getting closer and closer to 0, or the partial with respect to x, there's almost no change there. And you can see this purple graph is very close to 0 there, right? It gets very high as we get close to the x-axis in the positive direction, very low as we get close to the x-axis in the negative direction, but very close to 0 out here on the edges, which matches with the shape of this. right? You can play all the same games. Here's a derivative with respect to y, and you can play all the same games here. Now we'd be moving in the y direction, which is this green axis, in the positive y direction. So for instance, this is tricky to see. Let me do one quick thing. I should change this color. Let's make it something very different than blue rather than red. All right, so now, right, looking at this red graph, moving in the positive y direction is this way, right? I know it's a little tricky to see, but there's this hill here we're sliding down, and you can see all these very negative values on the green graph, right? They switch to positive over here, where if we move along the y direction on this red, we're going up, everything's very, very positive, right? Same thing out here. If we're moving in the y direction, this red is pretty flat out here, and you can see this greenish blue graph is getting close to 0 out there. So it's harder to look at and think about because of the fact that we're dealing with, you know, this extra dimension makes just drawing it harder and looking at it more difficult, but we get the same kind of relationship where we're looking at very steep surfaces, like steep hills. You imagine very high positive or negative values for our derivatives, depending on whether you're moving up or down and which direction you're moving in, right? It can get very confusing because you also have to think about which of the two directions we're dealing with are we moving in. Okay, just wanted to give a little taste of that. That'll do it for this one. Thanks everybody, and I will see you in the next video.